Hello everyone and welcome back to the channel. Today we are diving deep into one of the most elegant and powerful concepts in the world of machine learning, and that is autoencoders. In this video, we'll be dissecting the key concept and the fundamental mathematics behind these fascinating neural network architectures, primarily drawing from the structure laid out in this article and introduction to autoencoders. We're going to cover a lot of ground. We'll start by explaining exactly what autoencoders are, exploring their limitations, and looking at their typical use case with some practical examples. We will then get into the core mechanics. This includes a discussion on the role of activation function in the output layer and, critically, the loss function that drives the learning process. And finally, we'll wrap up by exploring the most common and powerful real world applications. We're talking about using autoencoders for essential tasks like dimensionality reduction, classification, denoising images, and even identifying anomalies in complex data. So get ready to unlock the secrets of autoencoders and let's get started. So typically when we talk about neural network, we are operating in a supervised setting. This means that for every input observation, which will denote as xi here, we have a corresponding label or an expected output value yi. The neural network's job is to learn the relationship between this xi and yi. But what if we shift gears? What if we only have unlabeled observations? This brings us to our training dataset ST, which is simply a set of m observations. Here, xi or each input xi is a vector in an n-dimensional space. So this is where autoencoder comes in. Autoencoders were first introduced in 1986 by Rumelhart, Hinton, and Williams. Their core goal is to learn a relationship that allows the network to reconstruct the original input observation x with the lowest possible error. Why would one want to learn to reconstruct the input observations? So this idea might initially sound confusing. Why would we train an algorithm to simply give us back what we put it in? So imagine you have a data set of images. An autoencoder would be trained to output an image that is as similar as possible to the input one. And if you're thinking there's no obvious benefit to this seemingly redundant task, you're right. To truly understand why autoencoders are useful, why we don't just copy the input, we need a more informative, though still general definition. So the key to autoencoders' power lies not in the output, but in the hidden layers. And that's what we'll discuss next. So to truly understand or grasp the power of autoencoder, we need a clear explanation. So the definition 1 tells us that an autoencoder is a type of algorithm with the primary purpose of learning an informative representation of the data. This informative representation can then be used for different downstream applications, all achieved by learning to reconstruct the original input observations well enough. To better understand this, we need to look at its typical architecture visualized here in figure 1. The autoencoder has three main components. The first is the encoder. This function takes the input and compresses it into a smaller dense code here. The second is the latent feature representation. This is the compressed code itself, a tensor of real numbers. This is the informative representation we just defined, and it's the real value of the autoencoder. Then we have the decoder. So this function takes the latent representation and attempts to expand it back from the into the original input. The encoder and decoder are implemented as neural networks. They are trained simultaneously with the goal that the reconstructed input is as close to the original input. The crucial insight here is that while the entire network is tasked with reconstruction, its real learning happens in the bottleneck, that is, the latent feature representation. Think about a handwritten number, like the number 4 that we see here. We humans don't remember the exact pixel gray values to recognize it. Instead, we extract essential information, like the number of lines required to write it or the angles where the lines connect. Similarly, the autoencoder also learns to create a latent representation that captures these useful and meaningful features. It forces the network to throw away any redundant noise and only keep the essential features necessary to recreate the original data. This compact, essential latent representation can then be incredibly useful for various tasks like feature extraction, for classification, clustering, or simply gaining a better understanding of the inherent structure of a dataset. The output is the reconstructed image, but the knowledge is in the latent code here. To formalize the architecture we just talked about, the encoder and decoder are typically implemented as neural networks. The encoder can be represented as a function g, which takes the input vector xi and maps it to the latent space or latent feature representation hi. Here, the input xi is in the real number form and the complex representation hi is in a lower dimensional space. The encoder maps from n dimension to q dimension. The decoder then takes in this latent space representation and maps it back to the reconstructed input xi dash using a second function f. So training an autoencoder is a simple optimization problem. We're trying to find the function f and g that minimize the difference between the original input xi and the reconstructed input xi prime or xi bar. This is expressed by the minimization of the loss function delta. Here, delta is our loss function, which is a measure of the difference or error between the input and the output. And the dot symbol indicates the average over all training observations. If we only focus on the minimization, it's possible to find f and g that perfectly reconstructs the output, essentially learning the identity function, where the output is exactly equal to the input. As we discussed, this is not very useful. We don't need a complex neural network to just copy data. To prevent this trivial solution and force the autoencoder to learn a meaningful latent representation, we use two main strategies: to create a bottleneck and adding regularization in the same form. The bottleneck is achieved by making the dimensionality of the latent feature lower, much lower than the input's dimensionality n. This forces the encoder to compress the information, keeping only the most essential features required for construction or reconstruction. This is the common case we'll focus on. But before we dive deeper into the bottleneck, we'll first identify the second crucial strategy, which is regularization. The second main strategy we use to prevent the autoencoder from learning the trivial identity function is regularization. Intuitively, regularization means enforcing sparsity in the latent feature output. We want most of the latent feature to be inactive or zero, forcing the remaining few to hold the most critical information. And the simplest way to achieve this is by adding a regularization term, such as an L1 or an L2 term, to our loss function. When using L2 regularization to our loss function, our minimum objective now looks like this. Here, the parameter theta I represents the parameters of our neural network functions f and g. In other words, the weights of the network. The term lambda controls how much we penalize large weights. By penalizing these weights, we force them to stay small, which promotes that required sparsity in the latent representation. Another interesting approach is to tie the weights of the encoder to the weights of the decoder, making them equal. These regularization approaches fundamentally achieve the same goal. They add sparsity to the latent space representation or latent feature representation, making the learned code more compact and meaningful. With both the bottleneck and regularization strategies in mind, we can now turn our attention to a specific type of autoencoder we will focus on, those built with feed-forward neural network that uses a bottleneck. This architecture is popular because it is both easy to implement and incredibly effective. We now turn to a specific architecture that is both widely used and highly effective, the feed-forward the feed-forward autoencoders or FFA. An FFA is simply a neural network built with dense layers arranged in a very specific symmetrical fashion, as you can see in figure 2 here. A typical FFA has odd number of layers and is symmetrical with respect to the central layer. Starting at the input layer, the number of neurons n1 is equal to n, the size of the input observation xi. As we move towards the center of the network, the number of neurons in each layer progressively drops. You can see that the middle layer is the smallest. The fact that the number of neurons in this layer is significantly smaller than the size of the input is the bottleneck that we talked about. This middle layer produces the crucial output Hi, which is our latent feature representation. In almost all practical applications, the layer that comes after the middle one, the decoder, are a mirrored version of the layers that came before, the encoder. For example, an autoencoder with 3 layers might have the following structure. In layer 1, we could have 10 neurons. In layer 2, or the latent layer, we could have 5 neurons. And in layer 3, or the output of the reconstruction layer, we could have 10 neurons again. All the layers up to and including the middle layer form the encoder, which compresses the data, and all the layer from the middle layer to the output form a decoder, which reconstructs it. So if the FFA training is successful, the output xi prime or xi bar will be a good approximation of the input xi. The essential takeaway is this: the decoder can successfully reconstruct the high dimensional input using only a much smaller number of learned features from a latent representation Hi instead of the original n features. This learned representation is the entire purpose of our autoencoders. In autoencoder, the final layer or the output layer of the decoder plays a particularly crucial role, and so does its activation function. The output activation function dictates the range of the values the reconstructed input xi bar can take. The most commonly used functions are ReLU and Sigmoid. We'll first talk about the ReLU. The ReLU activation function can assume all values in the range 0 to positive infinity. This makes ReLU a good choice when your input observation xi assumes a wide range of positive real values. However, if your input data can assume negative values, ReLU is a poor choice, as it will clip all the negative outputs to 0. In that specific case, the identity function would be a much better alternative. Next, we look at the sigmoid function. Its formula is given here. The sigmoid function can assume all values in the range 0 to 1. The activation function should only be used if the input observation xi are already within the range 0 to 1, or if you have normalized them to be in that range. Consider the MNIST dataset as an example. Each pixel's gray value is originally an integer between 0 and 255. By dividing all pixel values by 255, we normalize them to fall between 0 and 1. In this normalized case, the sigmoid function would be an excellent choice for the outputs layer activation. In summary, the sigmoid activation function for the output layer is the right choice whenever your input observations are scaled to be between 0 and 1. As with any neural network model, we need a loss function to minimize. This function must measure the difference between the original input xi and the reconstructed input xi bar. Our minimization objective for the autoencoder, which is trying to learn an approximation of the identity function, is to find weights that can minimize the expected loss. That is shown in this particular equation here. Here, the function g of the encoder and f of the decoder are obtained using the dense layers of our feed-forward autoencoder. Two loss functions are widely used for autoencoders. One is MSE and the other is binary cross entropy or BCE. Let's look at both, starting with the most common. First, we start with mean square error or MSE. Since an autoencoder is fundamentally trying to solve a regression problem, predicting a continuous output xi bar that matches the continuous input xi, the most common choice for the loss function is the mean squared error or MSE. You can see the formula for mean square error here in equation 9. Here, M is the number of observations and the symbol dot indicates the norm of a vector, which is essentially the length between the input and reconstructed output. The MSE loss can be used in almost all autoencoder types or cases, regardless of your activation function or how you normalize the data. It's easy to show mathematically that the minimization of this particular MSE loss is found when the reconstructed output perfectly matches the input xi prime or xi bar. The minimum is found when the partial derivative of the loss with respect to the input x bar j is equal to 0. By calculating the derivative and the second derivative, we can confirm that setting the derivative to 0 indeed leads to the condition xj equals to xj bar, and the positive second derivative confirms that we have found a minimum point. In short, MSE loss function directly guides the autoencoder to its goal, making the reconstructed output as close as possible to the original input. The second loss function we frequently encounter is binary cross entropy loss. This is appropriate choice when two key requirements are met. The first, the input features xi are normalized to be between 0 and 1. And the second, the activation function of the output layer is a sigmoid function, which also limits the network's output to be between 0 and 1. While binary cross entropy is used in classification problems, it works beautifully for autoencoders that deal with normalized binary-like data. The formula for binary cross entropy loss is shown in equation 14 here. Here, the term xji is the jth component of the ith observation, and the sum covers all observations and all components of the vector. But the question as before is, can we prove that minimizing this loss function is equivalent to perfectly reconstructing the input? To find where the loss has a minimum, we need to find the values of xi bar that satisfy the condition where the first derivative is 0. When we calculate the derivative of the loss with respect to a specific output component xi bar, we find that the equation is satisfied only if xi is equal to xi bar. This means the minimum loss is achieved exactly when the reconstructed output perfectly matches the input. Finally, to make sure this is truly a minimum point and not a maximum or saddle point, we must verify that the second derivative is a positive. After calculating and simplifying the second derivative, we find that the resulting expression is always greater than 0 within the valid range of xi bar, which is between 0 and 1. Therefore, the minimum of the binary cross entropy cost function is mathematically proven to be reached when the output is exactly equal to the input. The essential prerequisite to remember is that using the binary cross entropy loss function requires that the input must be normalized between 0 and 1, and the activation function for the last layer must be a sigmoid or softmax function. Now that we've covered the loss functions, we can formally define the reconstruction error. The reconstruction error is simply a metric that gives us a clear indication of how successfully the autoencoder was able to reconstruct the original input observation xi. The most easily calculated form of reconstruction error is the mean squared error, as we just talked about earlier. The concept is quite intuitive. When the reconstruction error is small, it means that the autoencoder successfully learned a compact representation and was able to reconstruct the input accurately. But when the reconstruction error is significantly large, it means the autoencoder failed to reconstruct the input well. This simple metric is extremely powerful, and we'll see later that the reconstruction error is used often as the fundamental basis for practical applications like anomaly identification with autoencoders. For example, if an autoencoder is trained on normal data, it will have a small reconstruction error for that normal data. If you feed it an anomaly, the reconstruction error will suddenly spike, telling you that something is wrong. You can visualize this. A low reconstruction error means the reconstructed image looks almost identical to the input, while a high reconstruction error means the reconstructed image is blurred or is missing key details. We will ground our point with a real world example here. Reconstructing handwritten digits using the MNIST dataset. The dataset contains 70,000 handwritten digits from 0 to 9. Since each image size is 28 times 28 pixels with only gray values, we have 784 features as input for our autoencoder. For our first experiment, we use a simple 3-layer autoencoder with a structure of 784, 16, 784. Notice the small middle layer of only 16 neurons. The first and the last layer must match the input dimension of 784. We train this model using the Adam optimizer and cross entropy loss. So if you look at figure 4, you can see that the top line contains 10 original random images from the dataset, and the bottom line shows the reconstructed images. The result is quite impressive. We have successfully reconstructed a 784 pixel image using only 16 features in the latent space. This powerfully tells us the essential information we needed to represent and reconstruct the digits is contained in a much lower number of features than the original 784. The autoencoder's ability to extract essential features is directly tied to the reconstructed ones from sorry. The autoencoder's ability to extract essential features is directly tied to the size of the bottleneck. The feed-forward autoencoder effectively performs the dimensionality reduction. If the bottleneck is too extreme, if the number of neurons in the middle layer is reduced too much, then the feed-forward autoencoder will fail to recreate the input digit well. For instance, look at the result when we reduce the middle layer to only 8 neurons, a structure of 784, 8, 784. In figure 6, you can see that the reconstruction is now clearly degraded. For example, the original 4 is reconstructed as something that resembles a 9, and the original 2 looks like a 3. The model simply couldn't squeeze enough relevant information into just 8 features. If we increase the middle layer size to 64 neurons, a structure of 784, 64, 784, the result gets much better. In figure 4, the reconstruction is nearly perfect as we see it here, confirming our expectation. Increasing the middle layer size improves reconstruction quality because the network has more capacity to store information. This improvement directly relates to the reconstruction error. As shown in figure 3 here, a small reconstruction error means a near perfect reconstruction, while a bigger reconstruction error means a poor, blurry reconstruction. Finally, we'll briefly compare our loss functions in practice. For those examples, or for these examples, we primarily use the binary cross entropy loss, but the mean squared error would have worked well as well. Figure 8 compares the reconstructed images from a model using BCE versus a model using MSE, both with a 16 neuron bottleneck. As you can see, the quality of reconstructed images is very similar, demonstrating that both loss functions are effective when correctly applied. We now arrive at the core use case of autoencoders, starting with their most intuitive application, that is the dimensionality reduction. As we have learned, the bottleneck methods means the latent features have a dimension that is smaller than the input dimension. The trained encoder part, by its very design, naturally reduces the input's dimensionality down to some real numbers. This learned compressed representation can then be used for various tasks like classification or clustering. A crucial point or critical point to make is the significant advantage of using an autoencoder compared to a more classical approach like principal component analysis or PCA. The main benefit of autoencoder approach is purely computational. It can deal with a very large amount of data efficiently because its training can be done using mini batches. In contrast, PCA, or which is the one of most widely used dimensionality reduction algorithm, typically requires calculating the eigenvectors of the entire dataset's covariance matrix at once. This provides a linear transformation of the features. The default PCA method uses a complexity of big O of d square for data. This is often not computationally feasible, and the algorithm does not scale well with increasing dataset size. In many practical applications where the data volume is enormous and the number of features is vast, the computational scalability of the autoencoder makes it a far more practical solution than traditional PCA. Furthermore, autoencoders are inherently more flexible as they can learn nonlinear transformations of the features, unlike the default PCA, which is strictly linear. It is a lesser known result, but an interesting one here. A feed-forward autoencoder or FFA is equivalent or is actually equivalent to PCA if the following three specific conditions are met. First, we use a linear function for the encoder. Second, we use a linear function for the decoder. And third, we use the mean square error of the loss function or for the loss function. This equivalence demonstrates that a basic linear autoencoder is performing the exact same dimensionality reduction as PCA. But by simply adding nonlinear activation functions, the autoencoder gains the power to learn far more complex nonlinear representations, making it a superior tool for modern day analysis. The core value of autoencoder lies in the informative intent representation it creates. The compressed feature can be extremely beneficial for classification tasks. We'll take a look at the example of classifying the MNIST digits. We have 784 pixel values for each image. If we use standard algorithm like k nearest neighbor directly on all 784 original features, the process is accurate but very slow. On the MNIST dataset, It takes around 16.6 minutes or 1000 seconds to run and achieve an excellent accuracy of 96.4%. However, what happens if we use the same KNN algorithm not on the original data but on the latent feature extracted by the trained autoencoder? For example, using the latent features g of xi from an autoencoder with only 8 neurons in the middle layer, the KNN classification runs in just 1.1 second. That is a gain of a factor of 1000 in running time. The trade-off is the loss of accuracy, however, dropping from 96.4 to 89%, a massive 7.4% drop. But the key takeaway is using only 8 features allows us to get a very high accuracy in just 1 second, making the classifier dramatically faster and more computationally efficient. We can see a similar trade-off with the fashion MNIST dataset. On the fashion MNIST dataset, using the original data takes about 16.6 minutes and gives an accuracy of 85.4%. Using a latent space representation of 8 features cuts the time to 1.2 seconds for 79.9% accuracy. Even increasing the latent features to 16 neurons, we achieve an accuracy of 83.6% in only 3 seconds. If we compare the 16 neuron result, which is 83.6% in 3 seconds, to the original feature result 85.4% in 1040 seconds, we see a minor drop of just 1.8%, but a running time that is 330 times faster. So in conclusion, using autoencoders to do classification with the latent features is a highly viable technique. It allows you to reduce the training time by several orders of magnitude while incurring only a minor acceptable drop in accuracy. This is why the encoder's output is so valuable in machine learning pipelines. We've established that using latent vectors or latent features for classification drastically reduces running time. But there is another more fundamental reason why we prioritize dimensionality reduction before many machine learning tasks. It becomes critical when the input dimension is very large, and that is the curse of dimensionality. This concept explains why high dimensional datasets are so challenging to understand. Let's consider the simplest possible example, a unit hypercube with d dimensions and m randomly spread out data points within it. We want to know how big must the side length L of the smallest hypercube be to contain at least one of these m points. The formula for the side length is given here. We'll use an example where m equals to 1000 randomly spread out points. If the dimension d equals to 2, meaning basically a square, the required side length L is only 0.003. The data is dense. But look what happens as the dimension increases. For d equals to 100, L jumps to 0.5. For d equal to 10, L jumps to 0.5. For d equal to 100, L jumps to 0.93, and for d equal to 1000, L is nearly 0.99. This table shows a dramatic trend. As the dimension increases, the required side length L must approach the full length of the hypercube, which is 1. This means that in high dimensions, the data becomes incredibly sparse. To capture a single observation, you need to consider almost the entire high dimensional space. The length or the gap between any 2 points in this massive space becomes indistinguishable from the maximum possible distance. When data is this sparse, any machine learning algorithm will struggle, as the relationships and the local neighborhood structures that many algorithms rely on simply disappear. We would need a number of observations far greater than the size of the most existing datasets to properly train a model. This is why the paper summarizes the key insight. Dimensionality reduction is fundamental in high dimensional dataset due to the curse of dimensionality. By reducing the data to a meaningful lower dimensional latent space, the autoencoder makes the classification problem feasible, efficient, and computationally practical. The final and most intriguing application of the autoencoder is anomaly identification. This is where the reconstruction error we discussed earlier becomes our primary tool. The core idea is simple. Train the autoencoder exclusively on normal, non-anomalous data. Since the model has only seen normal examples, it learns to reconstruct them very well, resulting in a low reconstruction error. When you present the model with a completely novel, unusual, or anomalous input, let's say an outlier, it struggles to reconstruct it because it lacks the necessary features in its latent code. This failure to reconstruct result in a high reconstruction error, which flags the input as an anomaly. We'll see a practical example using the MNIST dataset. We take our previously trained autoencoder, the one trained only on the 60,000 handwritten digits. We then create a test dataset by adding one image of a shoe from the MNIST or fashion MNIST dataset to the 10,000 MNIST test images. This shoe is an outlier because it's an entirely another image class than the handwritten data the model was trained on. When we calculate the reconstruction error for all 10,001 images, the shoe has the highest reconstruction error in the entire dataset with a value of 0.062. As you can see in figure 10, the autoencoder is completely unable to reconstruct the image. The reconstructed output is just a blurred, noisy shape. By contrast, figure 11 shows an image with the second biggest reconstruction error, a poorly written digit, which is significantly lower at 0.022. This massive gap allows us to confidently classify the shoe as a primary outlier. In general, anomaly identification using autoencoders follows a simple set of steps. First, train an autoencoder on a dataset known not to have an outliers. Second, for any new observation, calculate the reconstruction error. Third, sort the observations by their reconstruction error. And fourth, classify the observations with the highest reconstruction error as outliers. This is an essential assumption here. The outliers must be a negligible part of the entire dataset. If you train the model on a dataset that is heavily contaminated with anomalies or outliers, the autoencoder will learn to reconstruct those outliers and the technique will fail. Classic example of this application include finding fraudulent credit card transactions and fault detections in industrial environments, where anomalies typically represent less than 0.1% of total data. The autoencoder proves to be a powerful and effective tool for finding those needles in a haystack. While the anomaly identification process seems straightforward, high reconstruction error equals anomaly. It's essential to understand a critical caveat. These methods are prone to overfitting and can give unstable results. But what does this mean? It means training the same autoencoder with a slightly different architecture, often with a slightly different initialization or maybe a batch order, gives you different reconstruction errors and consequently identify a completely another set of outliers. This instability means you cannot blindly trust a single model's result when looking at anomalies. The simplest way to deal with this instability is to use ensemble methods. Instead of relying on one model, you can train several autoencoders or several different models. Then either take the average of the reconstruction error from all models or take the maximum of reconstruction errors evaluated from several models to make your final decision. This caution is critical here. Anomaly identification done with autoencoders is prone to overfitting and unstable result. It is therefore essential to be aware of these problems and compare the result coming from different models to interpret your outliers correctly. And with that final note on stability, we conclude our deep dive into the architecture and applications of autoencoder. Up until now, we focused entirely on feed-forward neural network architectures built with dense layers. While feed-forward autoencoders are easy to implement and work well, especially for structured data, there is no rule stating that this is the only way. When dealing specifically with image data, autoencoders built with convolutional layers known as convolutional autoencoders are often much more efficient and powerful. This is because convolutional layers are naturally built to recognize and extract spatial hierarchies and patterns within images, like edges, textures, and shapes. They maintain the 2D structure of the image, unlike the dense layers which flatten the input. And the results speak for themselves. In the paper's comparison between the FFA architecture 784, 32, 784 and the more complex convolutional autoencoders architecture, the convolutional autoencoder architecture clearly gives a better reconstruction results because it's optimized for images. The takeaway here is that feed-forward autoencoders are bad, but they represent the simplest starting point. For serious work involving images, convolutional autoencoders are a highly valuable or a viable and often superior solution, allowing the latent features to be modeled as a multi-dimensional tensor rather than just a one-dimensional array of numbers. The specific choice of architecture, dense or convolutional layers, depends entirely on your specific data and problem. And with that, we conclude our comprehensive look at this paper, an introduction into autoencoders. We've explored how the autoencoders is a remarkably elegant neural network designed for unsupervised learning. Its true power lies not in its reconstructed output, but in the compressed, informative, latent representation it learns through the bottleneck. This learned representation is a versatile tool enabling efficient solutions for dimensionality reduction that scales better than the classical PCA, classification that achieves massive speed gains by conquering the course of dimensionality, and denoising to clean up the corrupted inputs. And finally, robust anomaly identification using the reconstructed error as the primary signals to finding outliers. We also learned that feed-forward autoencoders are a great start. Professional image work often benefits from convolutional autoencoders. So, if you found this breakdown of autoencoders helpful, hit that like button and subscribe for more deep dives into machine learning concepts. Let me know in the comments what model you'd like me to cover next. Until then, keep learning and stay tuned. I'll see you in the next video.